Hi, Doc Revis here. In this video, I will carry out enthalpy calculations, delta H calculations, involving Hess's law. Let's do this by using some sample problems. Here's our first problem. What is a molar reaction enthalpy for the following reaction? The reaction is carbon plus water, giving carbon monoxide plus hydrogen. Carbon's a solid, water's a gas, and carbon monoxide is a gas, and hydrogen is a gas. To carry out these types of calculations, we will need standard enthalpy tables. These are found in many reference books and reference materials. In most Gen Chem classes, the professors will give you these values. So we have these standard equations. And here's how we work the problem. I suggest that you start by looking at the reactants and aligning them with a standard equation. What do I mean? In the target equation, carbon is on the left. It is a reactant. Therefore, I will choose an equation from the standard set of tables that has carbon in it, and I will position that with carbon on the left. In the case of this standard table, carbon is already on the left. It has a value of minus 605 kilojoules. Therefore, my first step then is to simply write this equation as it is with no change because the carbon is already located on the reactant side. Next, I'll go back to my target equation. I would choose water. I would then write the equation that contains water with it shown on the same side as the target. In this case, standard equation number 3 has water, but it's on the right side of the equation. It's on the product side. Therefore, I will flip that, and that means I also have to reverse the sign. Note also that in the balanced equation for the target, I have half the number of moles of water. Therefore, I have to also divide the standard equation 3 by 2. Therefore, I obtain a positive 319 kilojoules because I reverse the sign and I divide it by 2 based on the balanced equations. So now that I have my two reactants, I will check to see whether or not my products are located on the proper side. I notice neither equation 1, standard equation 1, or standard equation 3 will give me the products. Therefore, I use standard equation 2 so that I can locate carbon monoxide on the product side. In the standard, carbon monoxide is on the left. I want it on the right. I flip it. Therefore, I have to change the sign from minus 966 to a positive 966. And I also have to divide by 2 to balance the equation. Therefore, I have the values shown here. I then cancel out any of the species that do not show up in the target equation, and they must all be balanced. And in this case, we have 1 oxygen on the left side. We have 1 total oxygen, O2, on the right side. They cancel out. We have a carbon dioxide on the right, and we have carbon dioxide on the left. They cancel out. When I cancel out, I summarize this equation. I add the values, and I have my delta H for the reaction of carbon solid plus water gas, giving carbon monoxide gas plus hydrogen gas. Let's do a second problem. Use the following calorimetry data to predict the standard enthalpy change for the reaction of ethene with chlorine gas. We show you the target equation. It's ethene plus chlorine, and we get the corresponding products. We go to the standard enthalpy tables, and we find standard number 1, number 2, and number 3. We chose these from the table because they relate to the species in the target equation. We then start to manipulate these to match the reactants and products on the proper sides of these equations. So in the case of ethene, I take ethene first, and I use standard equation number 2 For it, because I have ethene on the left side, I simply write that equation, no change. I then look at my chlorine gas, Cl2. I use standard equation number 1 for that. I know that chlorine in the standard matches the reactant side with the target, therefore no change. I simply write this equation and I have a minus 185 kilojoules. Then I look for my product side and I note in order to get my product, I must flip, reverse standard equation number 3, and therefore I must flip, reverse the sign from a minus 140 to a positive 140. I record these values. I cancel out any species that do not show up in the balanced equation. I confirm that this is indeed a reasonable process for this. I add it together and I get a minus 110 kilojoules for this equation. There you have it, how to work Hess's law thermochemistry problems.